So my name is Balthazar Donon. I am a researcher at RTE from the Research and Development Department. And I will be presenting our work on trying to develop an AI assistant for the operation of power grids. And all of this work is based on graph neural networks. So this presentation is split into 3 parts. So first of all, I will try to motivate a bit our choice for graph neural networks. Then I will talk about 3 different use cases we are currently exploring. And then I will talk about the common framework that we use. The goal of this presentation is really for me to get an idea of how interested would some people be in taking a look at our code. So we are starting to think about releasing it as open source. So at the end of the presentation, there will be a small QR code that I invite you to scan. So first of all, let's motivate this choice for graph neural networks. So as you may already know, there is a huge transformation going on in the electric system. So there is the growth of renewable energy sources, the fact that nuclear power plants are going to take a smaller part in the energy mix in the future. We also have to renew some transmission lines because they are getting older and older every year. Also, the growth of consumption that we are envisioning for the next few decades, and the development of power electronics. So all of that is creating a really uncertain context for power grid operation, and also it is creating some new situations. So for instance, here you have a small picture of the voltages in France. So it was not so long ago. And in red, so you have some red dots right here, 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 and here. So it means that there are some over voltages, which is something we definitely want to avoid. And in orange, you have, it means that you are really close to the limit. So operating the grid is becoming more and more challenging every year, and we want to help operators deal with this growing complexity. So there are multiple ways of doing that. We could resort to traditional optimization methods, which are robust and reliable. Also, they come with some theoretical guarantees, which is super valuable. But also, they involve very large computational times, and they are really unsuitable for full-scale and real-time operations. So that's why we are investigating the use of AI, because they are very fast. So neural networks are able to produce prediction really quickly. So they are well suited for real-time operations, even though you do not have any theoretical guarantee, and even though the training can be extensively long and expensive. So here, more specifically, we are focusing on graph neural networks, which are a type of neural networks that are dedicated to graph data. And the power grid being a graph, it works quite well. So when I started my PhD at RTE in 2018, so 7 years ago, I took a look at the RTE data, and I observed that there was a huge variability in terms of topology. You can have changes in asset names, you can have some bus splitting, you can have some new assets that are coming inside the grid. And you can have some planned or unplanned contingencies in your data. So that's why I started right at the beginning of my PhD to focus on graph neural networks, which are able to handle this kind of topological variations. So here, I'm not talking about being able to generalize to some new topologies. I'm talking about being able to exploit the data we already have at RTE that display those large topological variations. Okay. So another aspect to this work is that we developed a formalism, a mathematical formalism, that can represent graphs, so power grids, as hyper-heterogeneous multi-graph, which are a very specific kind of graph And we have developed a companion graph neural network architecture that works on this kind of data. So that means that right now we have graph neural network architectures that are running on the full-scale RTE system and that work without any preprocessing. So we just have to import a file using PyPowSybl to extract all the relevant tables and then push it to our graph neural network. So let me say a few words about the typical use cases that we are investigating. So the most important one, I would say, is the tertiary voltage control problem. So as I showed you a few minutes ago, there is an increasing amount of high voltage events in the French grid. So we want to address that, and we want to help operators reduce those high voltage events. So to do that, we have multiple drivers for action, namely line activations. So we can disconnect some selected lines. We can also modify the voltage set points of ratio tap changers. We can modify the voltage set points of secondary voltage control, which basically amounts to modifying the voltage set points of some generators, to simplify. And also we can open or close some shunts in the grid. So the first results are the following. So we trained our model on a full-scale RTE system over 1 year of data. So it's the full 7K system, 7K buses system. And we managed to reduce the amount of overvoltages by a factor 2. Still, there is still a lot of work to do, so we are quite optimistic, but we still have to go further than that because there are still some issues regarding the robustness and stability of the training. So we are currently investigating this work. It's really an ongoing work. So in terms of technology readiness level, we are somewhere between 4 and 5, let's say. And the two key features of this work is that we are working in a self-supervised fashion. So the graph neural network is discovering by itself the relevant strategies to handle voltages. And also we are working in real scale. So we are working on the real-life data that we have at RTE. So I have another use case for you, which is called contingency screening. So it's really the beginning for us on this topic because we've been working on that for only 3 months. And for now, it's only a research internship, but we definitely plan to continue on this topic afterwards. So the goal is to accelerate the security analysis. So in order to perform the security analysis, basically you will disconnect all the lines or transformers to make sure that the network is able to withstand any possible disturbance, so that there is no overflow or overvoltage anywhere in the grid. So to do that, you need to perform n simulations, so n computations to test all the n-1 cases. Here we want to accelerate that by using a single graph neural network that will directly flag the contingency as risky or not. So it's really an edge-level classification using a graph neural network. So instead, once again, instead of having n computations, we only have 1. So the early results are quite good already. So we are once again working on the full RTE system. We are working on data that were extracted from the process we have for the contingency screening. So it is already labeled data. So we are working in a supervised fashion. It's really a classification task, so quite standard. And in terms of performance, we managed to correctly predict 95% of the risky outages. So of course, the goal is to go to 100%, but we have planned to improve the results. And of course, there are a lot of false positive, meaning that there are approximately 1,000 of non-risky outages that were flagged as being risky. So still, even with this kind of early results and early performance, we could manage to decrease the computational time by a factor of approximately 8. But some improvements should be coming soon. So in terms of technology readiness level, we are somewhere between 4 and 5, once again. So here, we are working in a supervised context. So we already have some labeled data, and we are working on the wheel scale system. So finally, the third use case that we are investigating, so it's also a quite recent project because we've been working on that for 5 months. It's related to topology optimization. So it's a very different approach from the 50 Hz approach. And here we are focusing on a specific use case, which is the maximization of the transfer capacity between 2 neighboring TSOs. So we are focusing on a very simple power grid that has only 12 substations. And we are trying to find the best possible state for each breaker within each substation. So it has a combinatorial aspect that is really, really large. So you have approximately 57 breakers in this small grid. So it's a very large space. But here we use a graph neural network to discover some new strategies. So this graph neural network is trained in an unsupervised fashion. And basically, by trial and error, it will discover some new strategies to operate the grid. So since it's a rather small system, we can use classical optimization. So we used a classical solver to compare ourselves. So it managed to increase the transfer capacity by 13.7%, and it can take a lot of time to solve these problems. So sometimes it's even it takes more than 10 minutes. And for our graph neural network model, it manages to improve the transfer capacity by 9.3%, and it takes a lot less time because it only takes around 200 milliseconds. So we are very optimistic about these results, even though we acknowledge that we are working on a very small-scale system and that there are many adaptations to be made to make it scale to the full RTE system. So in terms of technology readiness level, we are at 3, let's say. So it's still really a research phase. So once again, it is a self-supervised training, and we are working on a small-scale system, so not yet the full RTE system. So I wanted to present all these use cases to underline that they have something in common. Because here we are using the exact same framework, the exact same pipeline for all these 3 use cases. So I want to present this Argo framework that we've been developing internally at RTE. So Argo stands for Amortized Real Grid Operations. So real grid, of course, we want to focus on real-life data, even though sometimes we have to focus on smaller systems if the problem is really too complicated. Operations, because we are really dedicated to power grid operations. I mean, we are not trying to solve some forecast problems or anything. It's really related to the grid operation. And amortized, it comes from the amortized optimization literature, which basically amounts to say that we are dealing with optimization problems, but using neural networks, using tools from the statistical learning theory. So we are training models to solve optimization problems. So I want to show you basically what happens inside this framework. So I want to show you a very basic training loop that is used for all 3 different use cases. So first of all, we need to sample a problem instance. So let us consider, for instance, that we are dealing with the tertiary voltage control problem. So we sample one problem instance, so one power grid file from our database, okay? And we extract the graph structure from this case. So once again, we use PyPowSybl, so I know that there are some PyPowSybl people in the room, so thank you for that. So we extract this graph X, then we pass it to the graph neural network, okay? That is parameterized by a certain set of parameters theta, okay? And then it produces a decision Y. So for the tertiary voltage control problem, Y will include a voltage set point for every generator that is contained in X, and also some activation or deactivation of shunts stuff like that. So it could include some continuous or discrete variables. Then you pass this decision y to the problem instance, and basically your problem instance will have to compute a direction of improvement, so a gradient, basically. So the derivative of a certain cost function you are trying to minimize with regards to this decision. And then you pass this gradient to your model, you perform some backpropagation, and you update the parameters theta. So what's really interesting when you frame it that way is that you can see that there is a very simple delimitation between two worlds. So at the bottom, you have the power systems world, you have the use case world, where for each specific use case, you will have to implement a different data extraction process for getting X, and a different gradient computation process for computing this. But then the top part is really the graph neural network part. It's really the deep learning part that is not related at all to power systems. So it knows nothing about power systems, basically. So this common part is part of a package that we have developed, a Python package that involves a power grid data representation class. It also involves a small library of graph neural networks that are able to work on real-life data from, for instance, from the RTE system, and also a training loop and some additional stuff. Okay, so in terms of roadmap, as I said, I started working on this topic in 2018. So between 2018 and 2022, it was really an exploration phase. So we were trying to identify the potential of using graph neural networks when we apply it to power grids. One of the main outcomes of this phase was really this mathematical formulation that allows to work on real-life data, and also the companion graph neural network that we have developed that is compatible with this data. Then there was a validation phase, so between 2022 and 2024, where the goal was really to validate that it was all working well on the full RTE system, so make it scalable, and also try to apply it to a very specific use case, the tertiary voltage control. And then since 2024, we have entered a consolidation phase that has two different aspects, so development aspects and also research aspects. In terms of development, we want to consolidate the pipeline. We want to consolidate the framework, and we want to push these graph neural networks towards production. So that means including some good practices from DevOps and MLOps. So it has become something very different from the research that I was doing when I was in the exploration phase. But still, we want to keep on doing some research because I believe that the kind of neural network architecture that we are using right now are not the definitive version. There are some new ideas coming from the machine learning domain that we need to be able to capture and to incorporate inside our pipeline. So we want to improve the existing pipeline. We also want to explore some new use cases, some new applications for this work. And also we want to do some research on alternative graph neural network architectures. So to do all that, we have some strong collaborations with the Université Paris-Saclay, with the Université de Liège. We are specifically working a lot with Professor Louis Wenkel from Liège, and we are working also with Eftimios Karangelos from UCD Dublin. And we also have some help in terms of development from Datastorm. So I would be very happy if the people in the room that are interested in what I just presented could take some time to answer this small form. Specifically, we would like to identify whether there is some room for an open source code that does that. So, still here. So thank you very much for your attention, and I have approximately 10 minutes for some questions. There is a mic here. Thank you.
So my question is, how does your method differ from policy-based reinforcement learning?
From
Reinforcement learning.
Okay.
Yeah.
Yes, it's a very important question because it's not reinforcement learning, or at least not traditional reinforcement learning. What we are doing here can be interpreted as a form of single-step reinforcement learning. Here we are focusing on problems that have no sequentiality, no uncertainty, and that are basically open-loop problems. So open-loop decision-making problems. So we are not trying to get inside this reinforcement learning domain. Yeah, sorry for the microphone being so far away.
Yeah, Georg Minzer, 50 Hertz Elia. Thank you first for your very nice presentation. I have one question on the training data. I'm not so sure whether I fully understood that. You used historic data that you have access to. This is how you train your GNN. Could you elaborate a bit on that, especially on what you expect, whether it will be able to do or predict things that it has never seen before, as we are dealing with a transformation in our industry and the grids of the future will be different from those of the past?
Of course. Actually, this generalization capability is really one of the main motivations for graph neural networks, because it is able to adapt to withstand some topological variations that occur daily. So in terms of training, here what we did for these two use cases, so tertiary voltage control and contingency screening, is that we trained ourselves on past forecasts. So it's not operating conditions that actually occurred in the real life, but it was previous forecasts. And we trained on forecasts for a certain period of time, and then we tested our method on the future of this period of time. So we tried to see if this model was able to stay relevant for at least a short period of time after training. So we tried to do that. But we know, of course, that if we wait too much, of course, there will be a data drift. So you will start to encounter some new operating conditions that are too far away from your training set. So, of course, you would need to retrain your model. Maybe you would need to do some data augmentation by adding some noise over your injections so that you can have a broader support for your training distribution. Yeah. Thank you. Okay, any other question?
Can you please go to the slide about the contingency screening? So there was a pretty large, yes, this one, thanks, a large false positive rate, a small false negative. Do you have some sort of follow-up efforts try to explain or interpret the results to understand how the false positives especially come up from?
Yeah. It's a bit surprising that we managed to get such high results in terms of risky outages, but we are so bad in terms of non-risky outages. We are currently exploring this. It's really too early to say. We already saw some stuff that we could modify in the training phase to improve that. Yeah, it's an ongoing work. As I said, it's been only 3 months.
Of course.
So, but yeah. Once we get a better idea of how to improve that,
I can recommend at least trying Lime and Sharp. There are some interpretability indexes people use in the machine learning community. Sharp, SHAP, and Lime, LIME. So those are the libraries we use in our studies as well.
Okay.
When we cannot fully explain some of the results, you get some sort of sensitivity impacts from all the factors you put as input or interim training. Try to explore. And that would help a lot, I guess, in the end, to get to the 89% shooting up higher, hopefully.
Okay.
Thanks.
Okay, any other question? We still have 2 minutes. Ah, Sébastien.
Can you easily make the framework available to other?
Sorry?
Can you make the framework that you develop easily available for other to play with, or is it?
That's really the point of this presentation. So if people are interested in it, we would be happy to release it as open source. But we want to first identify if some people would be eager to collaborate. So that's the point of this form. So once again, if you did not already answer.
But it's not a trap. So basically, if they say yes, so it could be quick afterwards.
Of course, of course. Yeah, and we would be very happy to have some external contributors, because for now it's only an internal effort, but we definitely see some potential in building a broader community with other TSOs or research institutes. Yeah, thank you. Okay, I think we're done, but feel free to reach out and ask any question. Thank you.